pleasure for me to introduce my colleague from the University of Chicago, Pedram Hassanzadeh, who is an associate professor in the Department of Geophysical Sciences, as well as the Committee for Computational and Applied Math, and is the director, or the faculty director of the AI+Climate initiative at UChicago, and also co-director of the Human-Centered Weather Forecast initiative. Great.
Okay, great. Thank you so much for organizing this exciting workshop and for having me. So we are going through a second revolution in weather and climate prediction, and this is driven by AI. And in this area, there are some concrete examples for success, like in weather forecasting for several days, up to 2 weeks. And there are some very exciting advances about longer-term climate prediction, as you heard from Chris, Laura, and earlier from Anima. But I want to talk about here is how about things that AI hasn't seen during its training. Now, the first things that come to your mind could be extreme weather events, in particular events that are so strong and so rare that we haven't observed them, and they're not in our training set, but we know that they are physically possible. We call these the gray swans. These are events that are most impactful, so we really hope that AI models can forecast them and characterize them. I will mainly talk about these, but also there are other examples like tipping points, basically when you have a bifurcation. And if there is time, I'll show you even simpler phenomena where you can characterize them this way and AI models can have challenges with them. So I'm going to motivate what we are trying to do in weather and climate prediction in terms of uncertainties. And we know that in climate prediction, there are 3 sources of uncertainty, 2 of them also relevant for weather forecasting. So one is epistemic uncertainty, structural error, model error, basically inadequate mathematical or computational representation of the underlying physics. There is scenario uncertainty, uncertainty about how much greenhouse gases will be in the atmosphere. This depends on many things, including policy and politics. And then the internal variability uncertainty, the fact that we are dealing with a chaotic system. This is basically a signal-to-noise ratio problem. And now we have tools that we can use to visualize and quantify the relative importance of these uncertainties as we look at different predictions. We know that, for example, depending on the size, like whether you are looking at something global or regional or what variable you are looking at, the relative importance of these uncertainties can be different. But at the end of the day, for extreme events at the regional scales, things that are most important for adaptation and even mitigation efforts, these 3 uncertainty sources, they're all very important. Now, the challenge is that reducing the epistemic uncertainty requires better models, often higher resolution, slower models. But reducing these 2 require faster models to look at many scenarios or do longer and larger ensemble calculations. So that's really the major challenge that we have, that at the end of the day, you have to make some sort of compromise about which of these you want to really reduce. So since AI, particularly deep learning, came to our field in 2016-17, there has been a lot of interest in whether AI can be used to reduce these uncertainties. Now, most of the efforts focus on this, reducing the epistemic uncertainty, mainly by developing better parameterizations, closure models, and there have been a lot of advances. You heard from Laura, and as you know, it's a huge effort, the CLIMA project here, that have been making a lot of advances in this area. Now, in the past 2 years, there has also been a rising interest in using AI to reduce these 2 uncertainties by using these AI emulators that you already heard from Laura and Chris. And this basically leverages the fact that these models are very fast, so you can reduce these 2 uncertainties. And as I'll discuss, indirectly, you can also reduce this one. So this rising interest in using emulators is really because of this remarkable success that AI has had in short, medium-term weather forecasting. So you already heard about these. But basically here, the idea is, let's just train a big neural network that takes the current state of the atmosphere, a big matrix that has velocity, temperature, humidity, pressure, every 25 kilometers around the globe from the surface to the stratosphere, and predict it 6 hours or 12 hours later. And then you can put this back and you march in time. And of course, training a neural net means finding the weight and biases that you get by minimizing a loss function. And this approach was around since 2016 and 17 with some mixed success. But things changed a lot in early 2022 when this paper came out introducing ForecastNet. This is work that Anima led and my group, which back then included Ashish, our next speaker as a grad student, and a number of other groups contributed to this. And here we showed that basically by training this model on reanalysis data, observational derived data, 40 years of data, you can train a neural net that can basically match the accuracy of the best physics-based models, while this model was around 100,000 times faster, tens of thousands of times more energy efficient. And soon a lot of other tech companies jumped in, developed bigger models, and at this point, you see these models in the news. They outperform the best numerical weather models. As mentioned, now these models are operational. For example, the European Center has its own model called AI+. This is a plot from their website. You can gain half a day in the forecaster skill just by using the AI model. But again, this model is 100,000 times faster. And again, beyond the speed, there are a lot of other advantages that these models bring in democratizing weather forecasting around the world and many things like that. If there is time, I will mention some work we have done along those lines. And again, there are now a lot of these models out there. Okay, so now there's a lot of interest in pushing the lead times to subseasonal to seasonal time scales, and even, again, as you already heard, to doing long-term climate predictions. There are a number of ideas out there. One is to actually turn these models from an initial value solver that we use for weather to some boundary value solver. So here the idea is, for example, if you are building an atmospheric-only emulator, there is a vector here, S, that would include things like sea surface temperature, land, ice, solar radiation, and other things. If you are building a coupled model, like Chris mentioned, SST will be in X, so there are other forcing and boundary conditions you might want to impose. Now, one way that these models can be used, again, thinking about the uncertainties, is this. Let's say I train this model on a number of high-resolution physics-based simulations with different forcings. Let's say I can do 10 to 50 years of these expensive simulations. I train this model on that data, and then once the model is trained, then for an unseen set of forcing and boundary conditions, something that at least in an interpolation between the ones that were used during the training, the model is super cheap. I can do large ensembles, long runs, generate a lot of data, use this to look at how the tails of the distributions, let's say how heat waves over California or tropical cyclones over Florida might change with climate change. And again, the advantage of this is, of course, this emulator is never going to be more accurate than the physics-based model. We will always need better and better physics-based models. But this kind of approach would allow us to reduce the internal variability uncertainty and the scenario uncertainty. And because we can go to more and more expensive models, again, indirectly, they can use the internal variability uncertainty, the epistemic error. But again, this can be extremely useful for extreme events at the regional scales. But of course, all of these hinges on two major things. One is, as we train this model and we run it for a very long time, that it remains physically consistent, not just stable, but produces flow that is physically correct. And specifically for the extremes, we need these 500,000 years to actually have more information about the tails than these 50 years. And that's not trivial. You can sample a linear function 500,000 times. Doesn't mean you have more information. It's just a linear function. So the question is, these 500,000 years, would they have events with return period longer than the 50 years, and events that are physically correct? So in my group, in the past few years, we have been building a hierarchy of test cases to look at these kind of questions. It goes from things like Lorentz to a lot of turbulent test cases to actual weather and climate data. And we have been looking at some of these questions, and we try to use the hierarchy to basically go between scalability and understanding. In this talk, I'm mainly going to show results from kind of real-world data, but Karan, who just received his PhD in our group, he's here. He has a lot of results, similar kind of analysis with turbulent test cases. So the question that I'm going to focus on for the rest of the talk is, can AI models predict events that are rarer and stronger than anything they have seen in their training set? I'm going to call these events gray swans, basically kind of leveraging some of the terms that were used before about tropical cyclones. These are events that are physically possible, but in the short observational records that we have, or simulations, or whatever it is, we haven't seen them. Again, 40 years of era 5 data, we have seen some extremes. If we had just much longer observation of this stationary system, there are events here that are, again, more impactful. These are different from black swans, something that might happen once in the age of the universe. I don't expect the models to capture these, but these gray swans are the ones, because of their the high impact, we really want to be able to forecast and characterize. Now, depending on who you ask, people might tell you that the current AI models can or cannot do this. Those who say they cannot, they basically tell you that, well, rare events, we all know about data imbalance, events that haven't contributed much to the loss function. Again, training this model is all about this loss function. We are not going to learn them. If something shows up in the training set 1 every 10,000 samples, it could have little contribution to this loss function, so the loss will not increase, data will not be updated, you don't learn them. And these gray swans are sort of the asymptotic limit of these of the data imbalance problem. Said in a different way, this would require the models to extrapolate at the tails, and we shouldn't expect these models to do that. Now, there are people who believe that, well, no, the models can do that because there is evidence that these models are learning some atmospheric dynamics. So maybe by seeing weaker events, they can learn from them and forecast the stronger events. So we started trying to answer these questions, and we looked at one specific event, the rainfall in Dubai last April. If you saw in the news, this was significant flooding in Dubai. If you look at the distribution of rainfall in that region in the training set of these models, this is how it looks like. This is where this event was. So this was twice more rain than any rain in the training set of these AI models. So the question is, can these powerful AI weather models, the state-of-the-art ones, forecast this event? So I'm going to take a sip of the coffee, and I ask you, do you think these models can forecast this event? Who thinks they can? Okay, who thinks they cannot? Okay, some skeptics. So it turned out the models can actually do a very good job in forecasting this event. So this is just a movie of what actually happened. The shading is the rainfall. This is the circulation. This is what GraphCast did. You see that the model actually can get the location and a lot of things right about this. If I make a time series of the rainfall over Dubai, so the black line here, this is precipitation in era 5. What happened? The dashed line is the most rain in the training set. The blue line, this is 5-day forecast from GraphCast, and you see it gets the timing right, the amplitude almost right. In the paper that we have done full analysis of this event, and again, the models capture many things correctly. There is a second model here, the Fushi. It gets many things right, it just doesn't get the amplitude right. We have also looked at AIFS, a couple of other models. Most of them do a very good job in capturing this event. So frankly, we actually were a little surprised that the models can do a good job. Now, at the same time, the same research scientist Chiang was doing another kind of experiment with ForecastNet. And this is work that involves Jonathan Ware, who is sitting over there, and Ashish, our next speaker. So in this work, we were using the fact that ForecastNet is a wonderful model that's actually it's the cheapest model, and it's open source, very easy to do experiments with. So we trained 25 versions of this model. So we trained 5 versions just by changing the random seeds, where we just trained on the data everybody uses from 1979 to 2015. We call that ForecastNet full. We also trained a version that we removed any sample that included a category 3, 4, 5 hurricane, tropical cyclone anywhere around the world. So we removed those from the training set. We call that ForecastNet no TC. You lose 25% of the data when you do this. So we also, for control, trained ForecastNet RAND, that we randomly removed 25% of the data, but we made sure all the category 3, 4, 5 storms are there. So now the question is, can this model forecast category 5 storms? Those are gray swans. We know they're physically possible. They happen. I actually just removed them. But the question is that this model has never seen them. Again, people might say that the model can learn from category 1 and 2 storms that the model has seen, forecast category 5. So just to show you the results, so this is Hurricane Lee, category 5 storm. The black line here, this is what happened. This is the pressure. So the lower the pressure, the stronger the storm. This is the limit of going from category 2 to 3. This is from 4 to 5. You see that ForecastNet Full and RAND, they actually do a good job in forecasting the evolution over several days of the strength of this storm. So now the question is, can this one forecast this event? So again, I ask you, who thinks that the model actually can forecast this? Okay. Who thinks they cannot? Okay. Turned out the model absolutely cannot forecast this. So here, it actually, you see, it weakens the storm, and then sort of it saturates around that boundary between category 2 and 3. And we looked at 20 of these. It's always the same story, whether you start when the hurricane was category 1 or whether it has already reached category 4, it always fails. And it gives you the worst kind of error. It gives you a false negative. It tells you there's a category 2 storm coming while you are getting a category 5 storm. Okay, so we were confused because we were asking, how come it worked so well for the Dubai event? Of course, it was different kind of phenomena, different models, and it didn't work here. So we did 2 more experiments here. So we trained 2 more versions where in these versions, we only removed samples that had category 3, 4, 5 over only the Pacific Ocean or the Atlantic Ocean. And then I'm not showing the results, but it turned out the model, as long as it has seen it in one part of the world, it can forecast it well in the other part of the world. So we started thinking that these models can actually learn at least about dynamically similar events from other regions. So now going back to the Dubai example, this event actually had a simple dynamics, well-known extratropical cyclone coming, producing rain. So we made a histogram of the rainfall of dynamically similar events in the training set, and this is the distribution. Now we see that there had been, in the training set, many events with similar dynamics that happened before, so this event was not so special, and we started believing that, well, these models learn from other regions. To dig a bit more into that, we started looking at the receptive fields of the model, which is, you can get that by sort of looking at the adjoint of the model. And there you see that these models actually have a global, or at least non-local receptive field. So what's shown here is that this is the derivative of precipitation over Dubai with respect to different variables to do a 6-hourly forecast, which basically says that, for example, when the model tries to do a forecast of rainfall over Dubai, it actually looks at this, atmospheric variable from all around the world. Of course, as expected, it mainly used the local information, but it certainly used the non-local information. And there is nothing physical about this. You don't expect a 6-hourly connection between something here and over here. But again, the point is the model has a global receptive field, which means that during the training, when the model was learning to forecast rain over Dubai, it could look at other events in other regions. It's actually this, looking at these receptive fields, you can look at any model. This is one from AI+. You see that it's different, and these are really things that are about the architecture. As you change the architecture, you can see actually how the receptive field changes. But again, the receptive field is non-local, and in the sense that it can certainly look at the entire mid-latitude of the northern hemisphere. And we have found these adjoints to be very useful in understanding some of the stuff that these models do. So to summarize what I have shown you so far, so what we find is that these models cannot extrapolate. They cannot learn global gray swans, but they can translocate. They can learn from one region, apply it somewhere else. I keep emphasizing the importance of this dynamical similarity because the events these are not going to learn from any low pressure system. Even the NOTC had seen events with very low pressure in the extratropics. Those are the extratropical cyclones. But we know that the physics of tropical and extratropical cyclones are different, and that manifests itself in the state vector. When you look at joint distributions, you see that they are different, and so the model only can learn from these dynamical similar events. We did this, again, here with a couple of models, but we believe that this applies to any model because, at least the current models, because they have very similar learning principle. Kind of the supervised learning focus on the fast dynamics, so we think that would be a common problem. Now, you might ask, how many gray swans did the model have to see to actually forecast the gray swans? So we had a fantastic intern this summer, and what she did, she started fine-tuning the model with 1, 5, 10, 20, 50 of the samples that we threw out. And it turned out that just by fine-tuning on 5 samples, the model significantly improves. And with 50, it is as good as the model that had seen all the data, which is very encouraging. And now we are doing some work trying to understand what actually got updated in the model by this fine-tuning over very few samples that fixed the problem. Okay, so far, I mainly talked about short-term weather forecasting, but I motivated these questions by asking the question about if I train these emulators on a small amount of data, what happens when I do a long emulation? So, of course, this question is difficult to answer with era 5, when we have very limited data, even with complex GCMs. So we have been looking at the intermediate complexity GCM called PLASM. It has an atmosphere, simple model for land, for ice, and you prescribe the ocean. And this model, I can integrate it for 100,000 years. So that would be my ground truth. We also trained 2 emulators on the 100 years of data from this system. One is with SFNO, the spherical Fourier neural operator. The other one is with the Pangoose, the transformer model. So we trained them only with 100 years of data, and then these models are stable. You can run them for 100,000 years. So now we have started looking at the return period curves, which is what people, if you talk to an economist, that's what they like to see, for the extreme events in different regions. So here's just an example of rainfall over Florida. The black line, this is the ground truth. The red triangles, these are from the training set. So this is the most rain this model had seen in the training set over Florida. The dashed lines, this is the GeV fit. And you see that the emulators actually can produce some events with some rain more than what was in the training set. We have looked at them. They look like reasonable events. But you see that the frequencies are off. It's still better than GeV fit, but again, they can be off by at least an order of magnitude. And we have done a lot of work in looking at different events, heat waves, coldest snaps. Part of the problem is the whack-a-mole problem that Laure mentioned. There's always some regional bias somewhere. If you try to fix it, you can do bias correction, you can retrain the model, but again, that bias will pop up somewhere else. But even beyond that, I think it's important to keep in mind, this is really a lot to ask of an emulator, because to get this frequency right, the emulator needs to get the larger scale circulation, the precursor to an extreme event right, get the connection between the larger scale circulation and the extreme event correctly, and reproduce all of that with the right frequency. And we think that at least the current emulators, the way they are trained, may not be able to get that. But again, I think they do better than expected in some sense. Now, to fix some of these problems, something we have been doing is to try to couple some of these AI models with some mathematical tools that we have. For example, rare event sampling algorithms. They have been something that people have used in climate community. One of the kind of math methods that have been used are based on, let's say I have a physics-based model. I generate an ensemble. After a week or two, I stop the simulations. And if I have a way to know which of these trajectories have higher chance to go to the extreme events, I can clone them, branch out from them, and the ones that may not get to an extreme event, I can just terminate them. To do that, you need what's called a score function that would tell you how to do this. But if you have that, you can basically keep using this algorithm to nudge the physics-based model, which can be expensive, to only sample from the parts of the phase space that there's a higher chance of getting an extreme event. Now, this approach has shown some success for some kind of events. For example, there's this very nice paper from Freddy Boucher that they showed that in the same model PLASM, if you have 1,000 years of computing budget, you can reproduce the return periods of like hot summers with the 10,000-year return period. But this approach becomes very difficult when you want to use it for like heat waves and extreme precipitation, and a lot of events that we are actually really interested in. So in the work that we have done, and again, it's a collaboration with Freddy and with Jonathan and with Dorian and others, so we started using the power of these AI forecast models that in short term, they are cheap, they are skillful, they can produce huge ensembles. So we still use the physics-based model to generate the ensemble, but then we use the AI model to calculate the score function. So here, I stop, I generate an ensemble of forecasts, I use that to get me the score function. Based on that, I decide how the physics-based model continue or terminate an ensemble. The nice thing about this hybrid approach is at the end, what comes out of it, whether it's a sample or it's a return period curve, it's all from the physics-based model. Now, we can go further. We can now use these physics-based samples to fine-tune the AI emulator. We can do active learning and get emulators that would have less problems with the extreme events and great swans. I should say, I believe that you always need physics-based samples to train these models. Some people believe that you can have a generative model, generate a lot of sample for you, train the AI model with that. At least in some experiments we have done, and you can ask Karan, in 2D turbulence, you get model collapse. So everything collapses at the end. OK, so I don't know how much time I have, but OK, I have 4 more minutes. I want to show an example about another kind of problem that these AI models can have problem if they haven't seen something in the loss function. It really is about that fast and slow dynamics that Laura mentioned. But because of time, I'm going to talk about now a success example because I talked about some of the challenges with the models. But let me show you an example of where these models work so well. So this summer, a number of us at U Chicago, me, a colleague who is an economist and somebody in public policy, worked with the Indian government and provided AI-based monsoon forecasts to 38 million farmers. And so we basically benchmarked the existing AI weather models, found that some of them are skillful even to forecast the onset of the monsoon rainfall 30 days ahead, blended them, did real-time forecasting, and the government turned them into text messages in Hindu and other languages and sent them to the farmers. And it turned out the forecast was very useful. This year, the Indian monsoon had some weird behavior. It started early, and then it stopped moving, and then moved after 3 weeks. And this forecast was the only forecast that actually warned the farmers about this dry spell. And we have information based on surveys that the farmers who paid attention actually found it useful. So I think these AI models are extremely remarkable and exciting, but there are a number of questions, challenges, and opportunities that I think we should answer and work on them. I only talked about the rare events, but there are more. And I think the way to make progress is to combine AI, math, and physics to address this. And so it's some of the work we do, to mention. I'm developing better algorithms that's worked with Anima and with Becca. And I think Ashish is going to talk about some of the other exciting tools about the stabilities. And of course, doing this kind of work is at the heart of AI+Science. We already heard about many of these kind of approaches yesterday and today. And I just want to highlight the ecosystem that we have at U Chicago around multidisciplinary collaborations around climate, biology, astrophysics, and some of the other fields to do this kind of work. So with that, I stop here. Looking forward to your questions.
Thank you. Super interesting work. I was just curious in the case where you kind of remove the stronger tropical cyclones, which is just a really interesting way to approach the problem where you actually have the data to compare to. Do you think that you can say, take that data set where you remove the tropical cyclones, and it's maybe a much harder problem to approach, but is there a way you could, for example, reformulate the loss function? There's been some work on kind of non-dimensionalizing or learning kind of different variants of loss functions that would essentially make the problem more within the distribution. Have you explored ideas where you can kind of translate some of these kind of then out of sample events to in-sample events by kind of exploring what kind of information you would have to include in, for example, a loss function to make this more tractable?
Yeah, that's a great question. And that's something we have thought about. It's not that easy to come up with that right transformation, especially when it involves dynamics. I think thermodynamics can be easier. But when it involves dynamics, how to scale like a sample. We have done some work that we try to take the samples of category 1 and 2 and scale them in the right way to solve the problem. We have made some progress, but again, whether that can be done for heat waves and for extreme precipitation, for all kinds of events, I think that's something to be seen. If it's just a data imbalance problem, you can weight your loss function and there are things you can do, but then gray swans, something you have not seen, especially if the dynamics is different, like if it's like a tipping point, then I think none of those ideas would work. But for this, I agree that some kind of transformation of the existing samples might be helpful.
So there are certain kinds of extreme events that you think are more robust and easier to predict? I mean, you mentioned that if they've been seen some other parts of the globe, that's helpful. Are there any other things that you think make certain kinds of extremes more
yeah, that's a great question. So I think heat waves and certainly colder snaps, given that the coldest number mainly about advection, right? That the model probably has seen all over the place. And maybe they're more scalable. And even for heat waves, maybe not for the soil moisture feedback, but just the part that comes from advection. I think those events might even be more, I mean, the fact that you can learn from other regions and maybe extrapolate a little bit, I think they can do that. In the plasm work, with heat wave, we see the model actually can generate heat waves beyond what it has seen by a few degrees, but I think that's enough for a lot of applications. And when we look at the composites, they actually look very reasonable. So I think tropical cyclones might be among the most difficult ones, and I agree. We just wanted to make a point that there is this problem.
Hello, Pedram, for the last part of your talk on the work with the Indian farmers, so kind of two follow-up questions. So one, when you said the farmers found it useful, what does that mean? And then second, is 30 days enough for them to make harvest decisions? So if you tell them, provide them information about monsoons 30 days in advance, is that enough for them to make actionable decisions? Or do they need 60 days or 90 days advance to make harvesting or planting decisions?
So of course, the longer lead times, the better. But also the economists I work with, some theoretical work they do, they believe any forecast is better than no forecast. But again, there are a lot of assumptions that goes into this. But 30 days is actually very useful for the farmers. Even like 5 days can be very useful. But the way that it helped people was, so sometimes people, when they see the rainfall starting in Kerala in the south of India, there is a rule of thumb that this many days later in your region, the monsoon will start. And like last year, that was perfect. And so the problem is the farmers plant the seeds based on that, and then you get a dry spell, they lose everything. So the ones who paid attention to our forecast, they just didn't plant the seed in this what's called the false onset. So they waited for the actual continuous rainfall to start. So we have, like the economists have some people underground who survey the farmers and get information, and yeah. Okay, great, thanks.